Hi everyone, my name is Lydia and this is what I wish they had taught me about econometrics and introduction. In the previous video, we revisited the concept of the orthogonality and the projection matrix. Today, we're going to see a little bit more clearly the orthogonality condition and why it creates confusion among students. Today's video is orthogonality versus unbiasedness, and the main purpose of it is to make sure you guys never confuse these two conditions together. One of the main reasons why you see this confusion, and believe me, it's very common, is because of a very natural question that might come to all of you. Why do we need to assume that the x and the error term, the epsilon, are uncorrelated when the OLS already makes sure that the x and the residuals are uncorrelated? In this case, keep in mind the residuals, as we've explained in previous videos, we can either write them with a Greek letter and a hat on top to mean this is what we have estimated. But as I've already denoted, in some of the books, especially for instance the Green Book or the Mostly Harmless Econometrics book, you will see that the residual is actually denoted with a Latin letter E instead of the Greek letter with a hat on top, and the Greek letter is mostly and explicitly reserved for indicating the error term. So because of this distinction, so residual error, we're already getting a step closer to finding what is the difference between these two important expressions. So again, from now on, we're going to use either the E or the epsilon hat to refer to the residual. And we're going to use epsilon entirely to refer to the error term. And I want to remind you again, the error term is generated from a data generating process, while the residual is literally the difference between your true observations and any predictions that you make. So it's something that can be calculated, while the error term is something that cannot be calculated. So looking similar, completely different jobs. Now, we've seen that OLS minimizes the sum of the residuals squared, okay? When you take the derivatives and solve the normal equations, so the first order conditions, the final condition that we kind of get is that the x, and I'm going to write it here now in matrix notation, is that the x prime here times e, so again, the residual is equal to 0. What this means, every regressor is orthogonal to the residuals. This is true in any sample. And it is also what we call as a mechanical property of OLS, which means it holds even if your model is misspecified. Keep in mind, OLS is basically constructed to make this happen. So if you see that this is not happening with your data, it means something has gone really wrong with your OLS estimation. Now, what about this second condition that we have here? I'm going to introduce this term of like unbiasedness in this case. And the idea is that why do we need unbiasedness to be true? The thing is, unbiasedness will refer, and we will have sort of a checklist for it only if we look at the condition of how the error term, so this theoretical term, is correlated with your x variable. And unfortunately, for us to make the claim that our beta hat is predicting and is hitting on average, so to speak, our true beta, we need to make sure that this unbiasedness is fulfilled, okay? And that will come if this condition is fulfilled. However, this is not guaranteed by the OLS. So if you remember, for the first condition, it was what we call the mechanical property, and the OLS was constructed to make this happen. For the second condition, OLS is not guaranteed. And in fact, for this condition to be guaranteed, we need what we call assumptions about the real world. About the data generating process where this error term is coming, and basically something that the estimator cannot enforce by itself. Why the confusion? So if we know that the residual and the error term are obviously different things, and if we know that, okay, this is a mechanical property and I know OLS is constructed to make it happen, while the other one, I need certain assumptions, why do we still have a confusion? The confusion starts because in some books and in some cases you might see that the residual is approximated with the error term. The reason why you will see it is because in large samples under a correctly specified model, the residuals do behave like the true errors. But keep in mind here, I'm making a lot of conditions. I need a large sample, correctly specified model. And this is only true if assumptions, certain assumptions about the real world hold in the first place. So it's very restrictive. OLS may give you residuals that look uncorrelated with the X, even if the true errors are actually correlated with the X, which in this case would mean you have a biased estimator and your mechanical orthogonality is still holding, but you're not having a correct picture of what the real world is doing. So key message is, again, orthogonality will always be true because OLS forces this, but the unbiased condition will not be guaranteed and it must be assumed, and a checklist on certain assumptions needs to be run down. This distinction is very, very important. To trust OLS, obviously, you need more than just the algebra. You need the right assumptions about the world. I hope this was helpful and managed to dispel any confusion that you might have had in the previous videos of why do we write the orthogonality condition the way we do and why are we using the residual instead of the error term. And I'll see you in the next video.